Okay, so let's get started. So students in the Zoom call, if you have any doubts, you can probably raise your hand. Okay. Okay. This fan is too loud. Okay. Hey, do you mind if I switch off this fan? I am fine. Okay. Can this switch off? Yeah. Yeah. Okay. So let's get started. Again, welcome to the course finally offline. So it's finally good to meet you all in person and good to teach to human faces rather than tables and chairs in the room. Okay. So before going to today's class, let me discuss something that was related to one of the questions in the mid semester. So one of the questions was where a sinusoidal signal was given to the ADC, right? I think it was some 301 by 1000 or something like that, right? Something like this. And I told that the ADC was thermal noise limited and say the FNR was some 50 dB, right? And I was asked, I mean, you are asked to plot the discrete Fourier transform when you take the 1000-point DFT, right? And most of you had plotted the signal portions correct, that you got the first fundamental at this and let's say harmonics at 2 other bins. Okay. But now, of course, along with that, you are going to have thermal noise because I mentioned it's thermal noise limited. So you'll have all these bins corresponding to thermal noise, right? And I told we take a 1000-point DFT. So single-sided, you have 0 to 499, isn't it? So if let's say this is at 0 dB, the signal. So what will be this level if the SNR is 50 dB? I mean, I told SNR is correct, right? So see, the point is it's not just minus 50 dB, right? I mean, the total noise power must be minus 50 dB. That part is right, but most of you didn't realize the fact that the noise power is sum of all these bins, right? So if this level is some N naught, so N naught times you have total of 500 bins, right? So log of all this is minus 50, right? And that's how we get it. Okay. And in the next part, you were asked to redraw the same spectrum when you take a 2000-point DFT, right? So now if you take a 2000-point DFT in single-sided spectrum, you have total of 1000 bins, right? So again, the signal portions will change. It will become 602, whatever. That's fine. What will happen to the noise now? That is this this level. If let us say this was some, say I don't know, some N naught dB. That is this level. Let's say it was N naught dB. What can you say about this level? Yeah, it's half, right? Because it's the same power is getting spread over two times the number of bins here, isn't it? So if this was, let us say, some minus 50, I mean, I don't know, some 80 dB or something, just giving a rough number. I don't know the real number, but this will be minus 83 dB. Is that clear? Okay. And of course, you'll see that in practice, this is something you commonly do, especially if you're trying to send some signal that is very weak. For example, you might try to send some signal that is so low that it might be buried under the noise. Okay. So let's say you take some spectrum and take DFT. You might find that you're not able to find this signal at all. Okay, that's because this level is much higher. But the moment you increase the number of points, you'll find that this level reduces and you might be able to locate the signal. Okay, so yeah, so this is something that is commonly done when you take measurements or when you try to detect very weak signals and stuff. Okay. So yeah, so with that, let's get started. So let's just quickly brush up what we saw in the last lecture, which hopefully you had seen. So in the last lecture, we saw a technique to increase the speed of the ADC. And in this case, we took the case of a flash ADC. Right? And we saw that if you have two identical ADCs, by interleaving the two, that is by making the first ADC sample at these time instance, 0, 2 TS, 4 TS, and the second ADC at TS, 3 TS, 5 TS. you can multiplex these two outputs to get a full rate ADC running at a sampling rate of Fs, right? And of course, you can extend this to N ADCs also. In that case, to get an effective sampling rate of Fs, each individual ADC must be running at Fs by N, right? And we also saw the non-idealities that can arise in this kind of arrangement, which essentially comes from the fact that we have some kind of mismatch between the two paths, right? And of course, we can have mismatch in the offsets, mismatch in the gain, and also you can have a mismatch in this timing offset, right? Ideally, this should be sampling with the timing offset of TS, but because of non-idealities, you might be sampling at some delta T away or before, right? And you also saw how we can correct them. So this mismatch in this offset, as you saw for a 2-channel ADC, results in an additional tone at Fs by 2 in addition to a DC tone, right? And if you have an N-channel or NX interleaved ADC, you will have tones at all these frequencies. And the common practice to correct for them is to use some kind of digital calibration, right? And the idea is to look at the output spectrum and add offsets at the output so that the mismatch in the offsets gets corrected. And this kind of digital calibration is very commonly used in any mixed signal systems, because you'll find that correcting for any non-idealities in the analog domain is extremely difficult. So in mixed signal systems, you have a digital information, you have powerful digital processing, you simply exploit it, that's all. Right, and similarly, we saw what happens with gain mismatch. So with gain error mismatch, you saw for a 2-channel or 2x interleaved case, along with the input sinusoid, you also have a sinusoid at Fs by 2 minus Fin. Right, again, this can be corrected easily by adding gain parts in the digital domain. Right, again, you calibrate these digital gains so as to minimize the strength of all these unwanted subtones. And finally, we saw the effect of timing skew, where you sample with the offset of delta T. This again resulted in a very similar spectrum as you had for the case with gain error mismatch. Again, you'll have a tone at Fs by 2 minus Fin. So this should again be corrected in some corrected in the digital domain. And one way is to have, of course, okay, instead of doing a digital correction, one way to tackle this problem is to have a global sample and hold, wherein the signal is not changing. So for the entire duration, a signal is constant. So even if there is a mismatch in the timing offset, there is no problem. But of course, in reality, you might find that this might not be feasible in many cases, because one reason to go for time interleaved ADC is that you might not be able to realize a sample and hold operating at the full speed. So if that is the case, then this cannot be done. And you'll have to resort to some kind of digital calibration. And one way to correct for it is to have multiple phases of the clock, right? And you can select these multiple phases to feed to these other ADC so as to correct for the timing offset. And this, of course, is one arrangement by which you can generate multiple phases or multiple delayed versions of the clock. Okay. So in this class, let's continue our quest to improve the performance of the ADC. And in this case, we'll take a flash ADC. So in this class, we'll see how to improve the resolution of the flash ADC. Improve. Yeah. So let's say you have the ADC. Okay. And the simplest way to model this ADC is to say that along with the input, I'm adding a quantization error or the quantization noise, right? So the output is the input plus the quantization noise, right? So now let us say I have this kind of system. Okay, forget about an ADC. I have a system which is this. Okay. Now, if I have to improve the resolution of ADC, ideally, what do I want to do? I mean, ideally, what should the output V be equal to? U, right? I mean, so in principle, what should be done to the output to get U to the, I mean, U? Sorry? Right? So you simply add minus Q. So at the output, you get Q. But of course, when you have an ADC, this Q is not known, right? So you'll have like this. So how can you get an estimate, or how can you find Q? I have only these signals, right? I have the input of the ADC and the output of the ADC. From this, how can you find Q? Okay, I mean one trivial way is to do subtraction. So I'll take these two. I'll subtract it like this. I'll get minus q. I'll simply correct it, right? So this in principle, you see that completely cancels the quantization noise, and you can get an infinite resolution ADC, right? So obviously that's not going to work in practice, right? Because if that's the case, you can have an infinite resolution ADC. So what do you think is the problem, or what's the catch here? Why do you say that? In the subtractor, there is some additional errors. Okay, let's say you can implement the subtractor ideally. There is no additional offset added by the subtractor. Is there something more fundamental in doing this subtraction operation? Correct. No, sorry. Okay. So, right. So that's one thing. I mean, what he's saying is, see, this is an analog signal, right? Whereas this is the digital signal. So if you want to subtract these two signals, you need to cross the domain, right? So of course, one way is to convert this to digital, right? And do the subtraction in the digital domain, and you get a digital version. And another way is like this is a digital signal, right? Let me draw in another color maybe. So what I'll do, I'll convert it to an analog signal. So now this will be an analog signal. This is an analog signal. I'll do the subtraction. I'll get an analog output. But again, finally, I need a digital signal, right? So I'll have one more ADC here. Okay. So I mean, these two seem to be equally viable options. Let's see what is better and what is not. So let me. Okay, so first let's take the first option where I convert this to digital. So let me just redraw this. So I have U, right? I'll call Q1. Okay, so this is U plus Q1, and this is essentially the ADC1, main ADC. So now I wish to add an ADC here, right? Because I want to convert this to digital. So I'll add an ADC. This will add its own quantization noise, right? So let that be some Q2. Okay. Okay. So you understand till this point, right? We are doing the basic to improve the performance of the ADC. Correct. Basically, what we are saying that some signal U, in which we are adding this analog quantization noise. So basically, how we are going to improve the performance? The point is, if you don't have Q at all, you get an infinite resolution ADC, right? That's what we are trying to cancel Q. That's the whole idea, isn't it? I mean, the digital output is the analog signal plus an error added. I'm trying to cancel this error completely. Right? That way ADC's resolution will be improved. If there is no error, then right? That's the overall principle here. Is that fine? Is that basic idea clear? I mean, don't get into the practical implementations. Just look at it as a systems point of view. Let's say I have this system. I model this ADC like this. Right? If this is the way we model it, this way we can completely cancel Q. That's the idea we get, right? So let's see when we try to implement what problems we face. So as you mentioned, so again here we need to either convert this to digital, right? Or this has to be converted to analog and digital. So first I'm exploring this option where I'm converting this analog to digital. Okay, so for that I'm adding an ADC here. Okay, and of course this ADC will add its own quantization noise here, right? So the moment I do the subtraction, so what will be the output I get here? So what is the output here? Okay. Yeah, okay. Is that fine, right? You get Q2 minus Q1. Is that fine? Okay, so this is in digital domain. This is also in digital. I can simply add it. But if you add these two, what do you get? If I add these two signals, what do I get? Sorry? Q plus Q2, right? So I'm essentially not gaining anything. It is as if I'm taking this ADC and doing the operation, right? This way I'm not getting any benefit. So Obviously, this doesn't seem to be a great solution to move ahead. So let's try the other option where I convert this digital signal to an equivalent analog signal and then convert it again to digital. Is that okay? So let me draw that here. This is the first ADC. So here I have the analog signal. Now the goal is I need to convert this digital signal to an equivalent analog signal, right? So what I'll do is I'll add a DAC here, that is a digital to analog converter. Okay, and notice that this DAC, what essentially it needs to do is the following. The output here will be some kind of a digital code, right? So it will be some 0, 1, 2, 3, and so on, right? What we want is an equivalent analog voltage representation of these codes. Okay, because if you remember, the quantizer, what it's supposed to do is the following. It's supposed to see if the input is lying between a range of, I mean, some reference levels, right? Say VR1 to VR2, say VR2 to VR3, and so on. If it is this range, it is supposed to assign an analog voltage, say VO1. Here it will assign some voltage VO2 and so on. And this voltage is what we represent as the digital code, right? So this is essentially code 0. This is code 1, and so on. Okay. So what this DAC needs to do is find a mapping from this digital output 0, 1, 2 to these voltages. That's all. Okay. And as we'll see when we go to the implementation, this can be done without adding any extra error. Okay. Because all I need to do is, I mean, if simplest way is, I'll just say, if the code is 1, I'll have an output, say some V0. If the code is 2, I'll say the output is 2 V0. Right? That's all. So this DAC operation can be realized without adding any extra error. That's what I want to highlight. Okay. So now this is an analog signal. This is an.
You are saying that basically, if my input is 0, then I will be assigning a particular voltage V1 to it.
I mean, one simple way is to, let's say 0, 0 volts, right? Yeah. Of course, you can add an offset to this later, right? I mean,
so if I say voltage of 3, say 3 represent a voltage of 3 0.
Correct.
But it is still digital, it will not be digital, but still it will be digital.
No. This is the voltage I'm saying. This, see, this is some, let's say some, I'll say my step size delta is, let's say 1 millivolt. Okay, for example. So what I will say is digital code 0 represents 0 volts. Digital code 1, I'll say it represents delta 1 millivolt. Digital code 2 represents, say, 2 millivolts, and so on. Input of the DAC is this, right? This is the output of the DAC. Is that okay? Fine, right?
You are saying that 0, 1 millivolt, 2 millivolt is the outputs.
Correct.
But still, it's a digital because
no. It's discrete time, quantized, but still it's an analog signal.
Yes. Okay.
That's all. I mean, digital meaning you just it doesn't have any voltage, right? It's just numbers 0, 1, 2, 3. That's what we know. I mean, that's what is digital to us. This is quantized, but still analog. Discrete time, discrete amplitude, but it's an analog signal. Okay. So now I'll convert to this kind of format. Okay. So now I'll subtract these two. So now I'll get an estimate of Q1 here. Is that okay? It's fine, right? So this portion is done where we found the estimate of Q2. So estimate of minus Q1. Now I need to convert this Q1 to digital domain before adding here, right? Because this is a digital signal, right? So what I need to add essentially here is another ADC. Okay, but let us say this ADC, say it's a 3-bit ADC, and it's going to compare the input in this range, minus VREF to plus VREF. Q1 is the quantization noise added by this ADC. So what can you say about the range of values that Q1 will take? Q1 is the quantization noise, right? Minus delta by 2 to plus delta by 2, right? So what is delta for this 3-bit ADC? 2 VREF by 2 power 3. So essentially this Yeah, fine, right? So which means Q1 is going to span minus Vref by 2 cube to plus Vref by 2 cube. Is that fine? So now again, if you use an ADC here, this ADC will be operating in the same reference voltage level, right? So if you want to get complete resolution of this ADC, you want the input to also span the entire range, right? Because if the quantization noise here, you see it's only within this range. If you directly feed in, what can happen is this range might not even cross one of the threshold levels of the second ADC. Okay, that is quantization noise might be here. You might get a constant output at the second ADC, isn't it? Because I mean, you think about it, right? Only if the input spans this entire range, you'll get the all codes. Let's say from all zeros to all ones. 0 to all ones. Right? If the quantization, I mean, if the input to the ADC is within this small range, it can so happen that it might be within only one of the ports and output will be constant. You will not get a equivalent representation of the voltage, right? So the point is, I need to make sure the input to the ADC spans the entire range. So what should be done? No. That's what, this is a 3-bit ADC, but the input to the ADC, as we mentioned, has to span the entire range minus Vref to plus Vref. Only then we'll get the complete 3-bit, right? I mean, only if the input ranges this entire, I mean, spans this entire range, we'll get the ports varying, right? If the input is only within this range, it can easily happen that the input is not crossing these reference levels of the second ADC and the output will be constant. Okay. So you need to make sure that before feeding the signal, the input is spanning the entire range from minus Vref to plus Vref. Okay. So now what do you think needs to be done here? Right. What? Right. What should be the gain of the amplifier? 8, right? So I'll just say it's G. I'll write as 2 power 3. Okay. Fine. Now if I do this output is minus G times Q1, right? And minus G times Q1 will span from minus Vref to plus Vref. Okay. This is fine, right? So now I have the output of the first ADC. I'll call it V1. Right? This is the first ADC, right? Okay. So this output is say U plus Q1. This is my ADC2. So let's say it adds a quantization noise Q2. What will be the output here? V2. Sorry. Minus dq1, the input, plus q2. Fine. So let me erase this portion. Oh, okay. So remember, our original goal was to make sure that this Q1, I mean, the quantization noise added by the first ADC is completely cancelled. That's where we started this discussion from, right? So looking at these two ADC outputs, how do you think they must be combined so that Q1 is completely cancelled? Right? V1 times G plus V2. And the other way to write is, I'll just say, correct, that's all. V1 plus V2 by G. Okay, this is fine. So what will be the output here? I'll essentially have the input for sure. What will be the output here when you do this kind of combination? Plus Q2 by G, right? So now we can clearly see, right? This is definitely better than what we had earlier, right? So the quantization noise of the second ADC is now reduced by the gain here, right? And what is the gain here in this case? Yeah, 8. It's I light as 2 power 3. Okay, this is fine. So definitely this seems. Okay. Yeah. So if you take an ADC, if I say that it has a resolution of 3 bits, right? What does it mean? If the input is varying from the entire range minus Vref to plus Vref, we will get all possible 8 codes, right? But now I'm saying the input is not varying, or let me just draw that again. So this is minus PREF2 plus PREF. So I'll have, say, I don't know how many levels I've drawn, but so many levels are there in the ADC. I'll have different codes, right? Only if the input is varying this entire range, you will see all the output codes. But now the input is not spanning the entire range. What can happen is it will lie within this range, which means the output is simply going to be constant, right? You're not going to get a faithful representation of the signal you have at the input. Is that fine? So is this clear? So if you do this arrangement, you see that the quantization noise of the second ADC is getting divided by the gain here. Okay. So now, what do you think is effective resolution that we have achieved? Let's say Q2 is, let's say this ADC2 is 4-bit ADC. So Q2 corresponds to 4 bits, right? So Q2 by 2 power cube, how many bits do you think it corresponds to? Okay, so let's take a step back. We want to find this, right? So I told Q2 corresponds to 4 bits. Okay. If the quantization noise is reduced by a factor of 2, how many bits does it represent? What? Yeah, 1 extra bit. Is that clear? 4 plus 1, right? Because see, okay, one easy way to think is, see, Q2, what we saw, it was spanning from minus delta by 2 to plus delta by 2, right? And delta essentially was VREF by some 2 power, 2 power n, let's say. Okay, this is, sorry, delta, right? So which means this is spanning from minus VREF by 2 power n to. Is that fine? Now I'm saying Q2 is divided by 2, which means even this range will be divided by 2. So from this you can clearly see, right? This is essentially 2 power n plus 1. Okay. So from this, can you say what does this correspond to? 7 bits, right? It's 4 plus 3, total of 7 bits. Okay. So if you just take a step back and see, what we have done is we have taken a 3-bit ADC here, a 4-bit ADC, and we have put in such a way that overall we have an ADC of 7 bits. Okay. So let me read out the same thing in a format that's commonly, in a way that's commonly drawn. So this is my input analog signal. This is the first ADC. So this is the output of the first ADC, which is U plus Q1. Okay. In our case, this was 3 bits, right? And then what did we do? We need to subtract this from the input to get a representation of the quantization noise. So that I take the digital output, use a DAC. Okay, subtracting. So this is going to give me minus Q1, but I cannot directly feed it to the second ADC. So before that, I'll amplify it by gain G, which is 2 power 3 in this case. And this is fed to the second ADC. Right? I've read on the same thing. This is fine, right? So this is my output V2. And sorry, the final output must be combined in this kind of format, V1 plus V2 by G. Okay. So now let's say we generalize it. Let's say this is B1 bits. Okay. So what should be the gain here? Two per B1. Okay. This should be 2 per B1. Now let us say this has a resolution corresponding to B2 bits. At the output, what will be the overall resolution I get? Sorry, B1 plus B2, fine. So overall, this will realize an ADC with a resolution of B1 plus B2 bits. Okay. Yeah. Yeah, let's compare it also, right? So let's say he has a point. He's saying, okay, you have 2 ADC, so you're adding extra area. So let's compare the area. Right? Let's say you try to realize a 3-bit ADC. How many comparators you need? 7 comparators. For 4 bits, how many comparators you need? 15. How many comparators you have in total? 22. But let's say you try to realize 7 bits ADC using flash directly. How many comparators you will need? Okay, 2 power 7 minus 1, right? 127. Is that clear now? So you would have required 127 comparators if you just were to realize, what do you say, straightforward 7-bit flash. Okay. But by cascading or like by combining the 2 ADCs to get a 7-bit, we see that the number of comparators has reduced drastically. Okay. And this kind of ADC is called a 2-step ADC for obvious reasons, because you're doing in 2 steps, right? Okay. So let's now look at how this will be done, right? So this operation, so let me write it again. So the output needs to be combined in this format. Okay. And for the case we took, V1 was 3 bits, V2 was 4 bits, and the gain is 2 power 3, right? So let us say V1 some 3-bit output. Okay, I write as XX. Okay, or let's say X1, X2, X3. So similarly, V2 is some 4-bit output. I'll write Y1, Y2, Y3, Y4. Okay. So what will be V2 by 2 power 3? I mean, if I divide, yeah, 7 bits. So remember, this is a digital output, right? This is essentially zeros and ones, right? If I divide a digital number by 2, what will be the divided output? I mean, understand, right? If I have a digital output 1, 1, if I divide it by 2, what happens? Right shift, right? So yeah, so I'm right shifting 3 times. So V2 by 2 cube will be 0, 0, 0, Y1, Y2, right? And V1 was X1, X2, X3, right? So now if you add it, what happens? Sorry. I mean, this is V1, right? X1, X2, X3, some 3 bits, right? This is V2 by 2 cube, where I have 3 zeros because of the right shifting operation. I'm going to add these two like this. What happens now at the output? No, why X3 plus X2? No, there is no X4, right? I mean, this is Y1, Y2, Y3, Y4. I mean, I'm adding it like this, right? Okay, so okay, I understand. The question is, I could have written it like this, right? By aligning the LSBs like this, but the way I have written is I've aligned the MSBs. So why do you think I have done it? Written it like this? Why have I aligned the MSBs instead of aligning the LSBs? Okay, so let's say we have an ADC which is comparing the input from minus VREF to plus VREF. Okay, this is say 0 volts in between. Let's say it's a 4-bit ADC. I'll have Y1, Y2, Y3, Y4. What does this MSB bit represent? It's a sign of the output, right? It's a sign of the input, right? Because if you write the codes, what you get here, you'll have all zeros, right? 0, 1, 1, 1. From here on, it will be 1, 0, 0, 0 to 1, 1, 1, 1. Isn't it? Is that fine? So the MSB is essentially the sign of the input. No. Either ways, it's a sign. Or if let us say 0 to VREF, yeah. So if it is 0 to VREF, it essentially says if the input is greater than VREF by 2, right? I mean, I can even think of this as a sign, right? If it's greater than V of Y2, we say it's positive, less than V of Y2, it's negative. The point is, the MSB corresponds to the first decision you make, the coarsest or the rough estimate of the input, right? Is that fine? Now we have a 3-bit ADC. I'll have, let me write it here, x1, x2, x3. So in this, what do you think represents the sign or the coarse estimate? x1, right? See, here this represents the MSB, and this is the sign. This is the MSB, this will represent the sign, right? So which means if you want to add the two numbers, you need to make sure these two must be aligned. Is that okay? Fine, right? Fine. Any confusions? Okay. So that's why I made sure that I have aligned these two like this. Okay.
Sir, suppose if we are having a number, suppose 1 triple 0,
Hmm.
right? And if I'm asking you to add it to 1
Hmm.
so how would you add it?
No. You are going to conventional representation of digital numbers, right? If this is 8, this is 7, you'll add it like this. But the point is, this is, you should not consider it as 7, is what I'm trying to say, because you are trying to add these two outputs, which are essentially representing the same input. Okay, to clarify it, let's say I have 2 bits. Okay. So I'll have 0, 0. Let me. Okay, so I'll have 0, 0, 0, 1, 1, 0, 1, 1. Now, if I say I increase the resolution by 1 bit, I'll have additional levels to compare. So this will be 0, 0, 0, 0, 0, 1. Okay. So now if the input is lying here somewhere, you see that these two are same essentially, right? The only additional information you're adding is here, isn't it? So if you want to say this 0, 0, and you want to represent it as an equivalent 3-bit when you are trying to add it to this 3-bit output, or let's not take 0, 0, let's take 0, 1. Okay, this 0, 1, if you straight directly convert it to decimal, it's 1, right? But here, when you're trying to add it to this 3-bit output, you need to make sure this is preserved. Okay, so this will become 2, right? Because here, what is it? It is some 2 plus 1, 2 plus 0.
Basically, you are dividing this to again to 2 parts. So that is what we are trying to do.
Correct. I mean, simplest way to think is the sign, right? I mean, if I have plus 1, I mean, let's say plus 0.5 and plus 0.025, you will add it like this, right? You will not add it like plus 0.5 and 0.025 like this, isn't it? So the MSB is essentially giving you the decimal representation. That's all the point you can think. Okay, so that's why we need to make sure we need to align these two MSBs and not the LSBs. Okay, so the moment you do that, I'll be adding x1, x2, x3 with these 3 zeros. So the output I'll have x1, x2, x3, y1, y2, y3, y4. Is that okay? So now you see, right, this operation is very straightforward. What I need to do, I need to take the 3 bits from V1 and append the 4 bits from V2 and say this is my overall 7-bit output. Okay. So I just need to concatenate V1 and V2 like this. That's all.
Okay, original.
Yeah. Okay. X1, x2, x3 were the output of V1.
Okay, so basically we have to make the that, output same and adding extra bits. So the representation.
I mean, yeah, like you can think of it like this, right? So you had 2 bits, you would have just resolved this. The moment you go to 3-bit, you're adding an additional bit that gets added to the LSB. That's all. Okay, so let me just take this once. So just some terminologies so that things are set. So this is usually called the residue because it's like the residue or the error that is present in the input, I mean at the output. So for obvious reason, this is called residue amplifier because you're amplifying the residue. And this is usually referred to as the coarse ADC. And this is the fine ADC. Okay. I mean, because the output we saw was represented like this, right? V1 and V2. Okay. As we saw, MSB is a coarse representation of the input, right? MSB is a very coarse approximation of the input. So this is a coarse output. This is the fine output. Like you resolve it in finer and finer levels. That's all. Okay. Fine. So this is as I mentioned, this is called the two-step ADC or two-step conversion. And of course, you don't have to stop at 2 steps. You can increase the number of steps, right? So let's just do a 3-bit or 3-step ADC. So for 3-step ADC, it's same thing. So here, instead of having a normal ADC, I'll have a 2-step ADC. That's all, right? I'll have one ADC here. The second or the ADC following this will now be a 2-step ADC. That's all. So I'll just simply paste it here. Okay, so let me erase these.
So instead of using 3-step, instead of using 3-step ADC, you can simply increase the gain of the residue amplifier.
If you increase the gain of the residue amplifier, okay. Remember this, right? Yeah, what's the problem if you increase the gain? Huh? So yeah, okay. If let's say I have 2 power 4, what happens? I mean, this point is the quantization noise seems to be dependent on this gain, right? So increase the gain and reducing the quantization noise lower and lower. So what happens if I increase the gain? Correct, right? So remember, the reason why we chose the gain to be 2 power 3 is because we wanted the input to the ADC to span minus Vref to plus Vref. Right? This is the Q1. So only if I give 2 power 3, it will span the maximum. The moment you have a higher gain, that's going to exceed the quantizer limits and the quantizer will be overloaded. Okay, so we'll not get the right digital representation. Okay. Yeah, so let's just look at this 3-step quickly. Remove these things. So this is my ADC1. I'll say it's 3 bits. So sorry, B1 bits. I have the first DAC here. This, let's say it's ADC2. Oops, I need to have an amplifier here. So what should be the gain of the amplifier? Sorry, 2 power B1. Okay, I'll just call it G1. That is 2 power B1. So let us say this second ADC has a resolution of B2 bits. So this is my DAC2. What will be the gain of the second amplifier here? No, why 2 power B1 plus B2? I mean, you don't think of, you think of this alone as a separate ADC. Okay. When we just had this as a 2-step ADC, what was the gain we used for G2? No, the gain, this is B2 bits. I mean, let's say this is, forget about this part. I had only this portion. So this ADC is B2 bits. Okay, so what should be this gain? 2 for B2. Okay, so this will be ADC3. And let's say this has P3 bits. Okay. I mean, again, in practice, you can have the same ADC here. I'm just showing different resolutions to see how each one affects the output. That's all. Okay. So how do you think the output needs to be combined finally? I have V1, V2, V3. Can anyone take a shot? Okay. Is that fine? Okay. See, one way to think is assume that This is an ADC. I'll say the output here is some V2 hat. Okay. And that is some input plus some quantization noise. Okay. So if you just had a two-step ADC, how would you have combined the outputs? These V1 plus V2 hat by G1, right? Okay. But now what is V2 hat here? You just zoom into this ADC and see. What is V2 hat? I mean, so what is the input here? Sorry, input here. I mean, if I call the quantization noise associated with the first ADC as Q1, what is this? Minus Q1. I mean, okay. So this is minus G1 times Q1. Fine. So this minus G1 Q1 is given to this two-step ADC. Okay. So what will be the output? It will be the input to the ADC, which is this fellow. That is minus G1 Q1 plus, or okay, plus the quantization noise added by the last stage. Okay. Plus, let's say quantization noise with this is Q2, this is Q3. So what will be the final output? Q3 by G2. Is that okay? I mean, or if you don't want to go this, you think of it like this, right? This is not V1. This is V2, V3. Okay. If you want to combine these two outputs, how would you do the two-step ADC? This is the first stage, this is the second stage, right? So how would you recombine the outputs? Is that fine? Okay. So V2 is essentially what? V2 is this guy minus G1 Q1 plus Q2. Okay. So what will be this fellow? I have the input plus quantization noise here. So input is getting subtracted from input plus quantization noise. Take care of these signs. No, this is minus G1 Q1. Here it is minus G1 Q1 plus Q2. I'll subtract these two. What do we get? Minus Q2, right? So this essentially will be minus Q2. So this is minus G2 Q2. So V3 is minus G2 Q2 plus Q3, right? So you do this, V3 is minus G2 Q2 plus Q3. I'll have by G2. So the output is simply minus G1 Q1 plus Q3 by G2. Is that okay? So this is my V2 hat. So I'll simply put it here. So what do I get? V2 hat is minus G1 Q1 plus Q3 by G2 by G1, right? And V1 is simply the input plus Q1. So from this you see that Q1 goes off, right? And you are left with Q3 by G1 G2. Is that okay? Fine. So the output we saw is Q3 by G1 G2, right? And let's say B1 G1 corresponds to a B1 bit ADC. This corresponds to B2 bits, and this corresponds to B3. What is the overall resolution we get? Okay, B1 plus B2 plus B3. Is it clear? I mean, we just saw before, right? If you just had G1 was essentially 2 power B1, this is 2 power B2. So this is essentially 2 power B1 plus B2. So the overall resolution will be B1 plus B2 plus B3. Okay. And by the same, I mean, we can expand, I mean, we can use our knowledge about this. For a two-step, what you did, you appended the two outputs, right? So for a three-step ADC, what do you think output, how do you think the output should be combined? I have V1, V2, V3. Is that fine? So this will be V1, V2, V3. That's all. Okay. And one last thing. So yeah. So from here, notice what happens. I have 3 ADCs, right? Each adding separate quantization noises, right? At the output, what you see is the quantization noise of Q1 and Q2 are getting cancelled completely, right? And the quantization noise of the last stage is getting divided by the gains it is seeing completely till the input. Okay. So we can extend the same thing for an n-step converter. So what do you think will happen in an n-step ADC? I have say ADC1, ADC2, and so on till ADCN. Yeah. So finally, if you combine the outputs correctly, you will have the last ADC's quantization noise divided by all the gains it sees before. Okay. And how, if the individual outputs are V1, V2 till Vn, how do you think they should be combined? We can take a look at here, right? So how did we combine here? So I'll expand it. So you'll have V1 plus V2 by G1 plus V3 by G1, G2. I just took this portion, put it here. Okay. So from this, can you say how the output of the n-step converter will look like? I mean, how should that be combined? I mean, here, see, first ADC is V1. Second ADC's output is scaled by the gain that you are adding here. Third ADC's output is getting divided by the gains it sees before. So how do you think for an n-step converter it will look like? Okay, is that fine? So V1 plus V2 by the gain it sees before, plus V3 by the overall gain it sees before is G1, G2, plus till last G1, G2 till Gn minus 1. Okay. So again, the overall resolution in this case will be, if G1 is 2 power B1, this is 2 power B2 and so on. And this corresponds to some Bn bit ADC. The overall resolution will be Bn plus B1 plus B2 till Bn minus 1. Okay. So yeah, we can stop at this point and meet next class. And does anyone have a class now? Can I take a couple of more minutes? You have class, okay.